Alright, so another thing that I've been playing with is finding a simple to express reasonable approximation for the perimeter of any given ellipse. Okay, right. So this is like the classic solution to this. They're infinite series, and mostly they're pain in the ass, and you need generally quite a few terms, each of which is terrible, in order to get reasonably good approximations. Okay, so that's the context. That's what I'm working with. But it turns out it's the basic idea of what we need to do is pretty simple. When the eccentricity, so we're working, the eccentricity is your basic variable here. When the eccentricity of the ellipse is 0, you just have a circle, so its perimeter is 2 pi times the radius, or pi times the diameter. Either way. And when its eccentricity is effectively 1, it's not really 1, when it's like 1 minus L naught, as the limit approaches 1 from the left, your perimeter becomes 4 times the radius, or 2 times the diameter. And you can see here I'm assuming we're using the radius, right? Because basic trig functions operate with respect to that, so that's what we're working with. This is what I came up with. And originally here, and it's a slightly worse approximation, what I had here was simply 2 on pi, or the inverse of pi on 2, which you notice is occurring elsewhere. That form works pretty nicely, and it's quite elegant. This is just slightly more accurate, so this is what I'm going with right now, and it's not too much more of a pain in the ass, so you wouldn't want to do this manually. 2 on pi might be easier if you're trying to do this manually, but it's still going to be a royal pain in the ass if you're doing this manually regardless, so I'm just going to assume you're not doing this manually. But this one expression right here, it keeps us, up until you're really, really close to your eccentricity being 1, it keeps you below an error below about 0.1%. So this is more accurate than most people are even willing to approximate the value of pi. So I feel like for general purpose, this is a perfectly practical formula for the perimeter of any given ellipse. Okay, and all we're doing, what we're doing basically is what we need to do is we need to move from the perimeter of a circle to the perimeter of that straight line segment. And what we need to do is we need to control the rate of change between those two. That's the only thing we need to do. Okay, we don't need to figure out what the integral of the equation looks like, because you can't do that. We don't know how to do that, except at specific points, like when the eccentricity is 1. But ironically, that yields a bunch of tangents. It's like whatever, but the angle is pi on 2, so that tangent isn't defined anyway. So ironically, you get all of this nonsense, and it doesn't even help you. And it's for the trivial solution where we know what the value is anyway. So yeah, here I'll run this. So it varies. I have it. So it's using k, right? So what it's going to do is, and I have k being the eccentricity. I don't like using e because it looks like Euler's constant, 2.71828, etc. I don't want to use that because it can be confusing, especially since we have exponents in here. I'm like, I really don't want that, because I will come back to it and be confused myself, because I'll forget what the hell was going on. So I'm using k to represent eccentricity. And there's some other things I was playing with here. This refines it significantly further, this value. If we just put it right in there, we do get a refinement. But I feel like it's not worth the complexity that this adds. So I'm going to leave it off. But here, you can see what's happening. This red line is the equation, the exact equation, whose integral, if we could take it between this line, the 0, and this line, pi on 2, if we could take that integral, that would give us the perimeter of the ellipse exactly. And the green line is what the perimeter of the ellipse at any given k is. And you can see it's moving between this point and this point. Those are our reference frames, right? And this is the equation that we get as the integral of this guy at pi on 2. So here, let's let it roll. So you can see that the way the green line is coming down, it is mimicking the rate of change of this space down here. That's what we want. And then right there, k is 1. Right there, the area under this curve is exactly 1. That's what we want, and that's exactly where this one ends. Okay, so if you're trying to do the general integral, what you're looking for is like, how does this blue line shift from being this straight line to being this guy, this tangent function? How does it move between those spaces? But really all we need, because when we're taking the integral, we're evaluating it here, and we're evaluating it here, and we're subtracting this value from this value, and then adding the constant of integration, which in this case we're just going to ignore. But the nice thing is, here they're all 0. So when you subtract it off, it doesn't matter. So really, all we need to do is look at what's happening here. Okay? So that's what I did. I took some calculations, and I measured it. I measured how it's changing. Okay? And naively, that looks like a circle, maybe. It looks slightly flat, but it's very, very close to a circle. So I was like, okay, let's just try that, see how accurate that is. It's not terribly accurate because the circle comes out to like over here somewhere. Like that error is pretty big out here. But for just a real simple approximation, that's, you know, it's within like 10%, something like that. Like, that's not horrible. It's not great, but it's not that horrible. But then for reference, so this is the actual data. This is the measured data. This is the curve generated by, so I'm about to blink it in, generated by this equation here. Well, it's probably this one. It doesn't really matter. It's this part. It's this part, really, right there. This part is what I'm going to map over this right now. So it's this little faint red line, and notice here that, you know, it's a little bit over, and then it's real close in this regime right here, almost spot on, and then it goes over a little bit down towards the end there. And this is actually where it's the worst, because that vertical difference is proportionally very significant, right? Because as we're running out of vertical space here, being a little bit off gives you a very big proportional difference. So out here, we're off by, it turns out it can be off by a few percent. Over here, we're off by like 1/5%. Like, this is real accurate. This is real close. This is real close up here. Like, for reference, this image is 512 pixels tall. And that height right there, it's like 2 pixels. Right, so we're at about a 1/10%. Or, I don't know, you do the math. Whatever that gives you. Whatever that gives you. But this is hugging it real close. And your equation is simply this. It's simply this. Your perimeter is this relative to the radius. Well, in this case, it would be the semi-major axis. Right, the semi-major axis times this. Or 1/4 of your perimeter is the semi-major axis times this. Which, I feel like as simple as this is, compared to your alternatives, this is unreasonable. This is unreasonably nice. Right? This is very, very pleasantly nice. And the degree of accuracy is comparable to saying that pi is like 22/7. It's in that range of, this is a very reasonable approximation. And it's usually an overestimate, which means like if you want to build an ellipse out of some material, you're going to end up having some extra material on hand, which is okay. I'd rather have slightly too much than not enough. Right. So in terms of practicality, this is very nice, I think. It is not a perfect representation. It is not a perfect fit to exactly finding the perimeter of any given ellipse. And as your eccentricity gets very close to 1, it gets significantly worse. But you have to be very close to 1. Your eccentricity has to be very close to 1 for it to really start being a problem out here. Because that's over in this regime right here, where the line is above the blue. The red line is a little bit above the blue. But over here, this is probably where most of your ellipses are going to occur anyway that have any interesting properties. Over here, it's real accurate. The precision that we're getting here is very, very high. And there's a couple times where it crosses the curve. So there is actually a few times, 2, I think there's 2 times. Well, plus the trivial. So at the ends, it's perfect. And then there's 2 times in here where it crosses. Because so like right in here, it actually slightly goes under the blue. The red line goes slightly under the blue. And then it comes back over. So it crosses twice over here. So you get a perfect approximation for 2 ellipses. And you get a perfect approximation, or an exact answer for the circle and for the straight line. Yeah. So all told, I think this is quite nice.